This is lecture 5 from chapter 9, picking back up with covalent bonds. So last lecture we were looking at multiple covalent bonds, specifically looking at double bonds. So for some elements you can have more than a double bond for covalent bonds. So we can have a triple bond. And that is where you've got two atoms sharing 3 pairs of electrons. This is obviously not as common as a double bond. This mainly occurs in compounds containing carbon and some nitrogen compounds. And this is a great example of this is acetylene. So you can see acetylene being used over here. So acetylene burns at incredibly high temperatures, and this is actually because of the multiple covalent bonds, because of this triple bond. That triple bond stores a lot of energy, and when it is burned, it releases a lot of energy. So this is what a triple bond would look like. So if you did it as a dot diagram, you'd have 3 sets of those electrons being shared in the center between the 2 carbons, and then 1 on either side. For the hydrogen, this is actually what acetylene looks like chemically. And so if we were to draw this instead as the covalent bond diagram with the lines, triple line between the carbons, and then a single line between each of the hydrogens, so that you've got the total for the 4 bonds for the carbon, and then the single bond for the hydrogen on each side. So the last thing to talk about as far as this, just the general covalent bond, is valence. So valence is just the number of covalent bonds that an atom can form. So the valence number, we've seen this a couple of times. So carbon valence, the carbon valence is equal to 4. So that means that it can, as we've just seen, form single, double, or triple bonds, and it can do this in combination. So in a compound, it can have double and single bonds, or it can have a triple bond and single bonds, depending on what elements it is combining with. Nitrogen has a valence of 3, because it's got the ability to make 3 covalent bonds. So it has the ability to make single, double, or triple bonds. Oxygen has a valence of just 2. So it can form single or double bonds. And then hydrogen has a valence of 1. So it only has the ability to make single bonds. Now, other elements obviously have valences as well. But these are the 4 that I've got listed because these are the 4 that you most commonly run into when you make covalent bonds with making covalent compounds. So these ones are the ones that we most commonly use. So let's do a little bit of practice. So we're going to make bond diagrams, not dot diagrams, but bond diagrams for some compounds. Now, when you're doing these, what I recommend is actually, if you're not really confident with making the bond diagrams just straight out, you can work on making the dot diagrams and then converting them to bond diagrams. So, for example, we've got carbon monoxide. Now this one, you're going to make the bonds based on the element that has the lowest number of available bonds. So we just saw carbon can make 4, oxygen can make 2. So that is going to get us carbon and oxygen with 2 lines in between. Now, I know you might be thinking, but carbon can make 4 bonds, and yes, it can. You can make carbon monoxide. It's not a super stable compound, but it is one that can be formed. You can also have nitrogen oxide. Again, it's going to be based on the element that has the lowest valence number, the lowest number of available bonds. And again, it is going to be oxygen. So this one would be N and then O with the 2 bonds in between, even though nitrogen has a valence of 3. So here we've got nitrogen with a valence of 3, and we've got 3 hydrogens. So if you weren't sure, you could, like I said, make a dot diagram. So you know that nitrogen has a valence of 3, which means it has 5 electrons in its outermost its outermost shell. So we've got 1, 2, 3, 4, 5. And so that means that you'd have a hydrogen on 3 sides with the bond pairs of electrons. So if we take this and convert it into a bond diagram, then it would look something like this. All right. N2, so this is the diatomic form of nitrogen, so the nitrogen gas. So we know it's going to be N and N. And since it's just those 2, you know they're going to share the electrons. And we know that nitrogen has a valence of 3 because it has those 5 electrons in its valence shell. So it's going to be 3 bonds in between. And then oxygen, we're going to have O and O. And as we saw up here, it's got a maximum of 2 bonds. So we're going to bond it together with 2 bonds. All right, so I mentioned that those atoms that are participating in covalent bonds become electrically neutral, but sometimes the bond itself can actually get a charge to it, and that's what we're going to look at next, what we call bond polarity. So you get some of the covalent bonds as what we call non-polar covalent bonds, and this is where the electrons are shared equally between atoms. So the electrons go back and forth between the atoms equally. So a great example of a nonpolar covalent bond is hydrogen. Another one would be something like oxygen. So the electrons are going to be shared equally between these guys. So the electrons are just going to go back and forth, and you don't end up with any sort of charge on the molecule because those are going to be equally distributed. On the other hand, you can get polar bonds, which are sometimes referred to as a dipole. And this is caused by an unequal sharing of electrons between atoms. And so you can see here, very different. So now we're looking at hydrogen and fluorine. And what we've got is an unequal distribution of electrons. So hydrogen only has that 1 electron of its own. It's sharing 1 with fluorine. But remember, fluorine has a lot more electrons to start with. So it's sharing 1 electron with hydrogen, but it has its own group of electrons already. So we're going to have a lot more of the negative charge building up on this side of the covalent bond because you've just got more electrons on that side. So what this is related to is what we call electronegativity. This is actually the ability of atoms of an element to attract bonding electrons. So it's not just the amount of electrons that an element can have that will create this polarity, but also the atoms themselves. So some of them are just really good at pulling electrons away from the atoms that they're partnered in a covalent bond. So the higher the value, the greater the attraction. So the higher the value of electronegativity something has on the periodic table, the more it's going to attract the electrons. And so we can use this to determine if a bond is going to be ionic or covalent. So let's take a look at how we'd figure this out. So if we take the values between the two elements and we subtract them and we get an absolute difference, meaning it doesn't matter if it's positive or negative, but the absolute difference between the two numbers. If the absolute difference is 1.7 or greater, that means we're going to get an ionic bond. And I'll show you what this means here in a second. I've got a table on the next page. So you've got 1.7 or greater, and that's going to get you an ionic bond. Between 0.5 and 1.7, that's going to get you a polar covalent. And anything less than 0.5 is going to get you just a regular covalent bond that is nonpolar. So let's take a look at, this is just showing you what this looks like as far as electron distribution. So this is a regular covalent, a nonpolar bond. So the electrons are distributed equally. A polar covalent bond where you've got more electrons on one side than the other. And then an ionic bond where they're actually separated. You've got a positive and a negative, but the two atoms are actually separated from each other. They're just drawn together because of that difference in their charge. So here is the electronegativity table, and if you need these values, I will provide these values for you. And so the difference in electronegativity, like I said, is going to help us predict the bond type. So you can see I've provided the little table down here so we can give this a try. And you can see on this table they've actually rated the numbers based on the height of the columns for our periodic table. So you can see hydrogen is kind of high, but the highest electronegativity is fluorine. So anything that is going to be in a covalent compound with fluorine, that is going to tend to make a polar compound usually. We'll see how that works when we look at some of these compounds. So you can see there's variation, but the electronegativity generally goes from lowest down here at francium in the corner, and then as you go across and up to the right hand corner, it increases. The exception is up here with hydrogen and beryllium. These guys are a little more electronegative than we would expect considering where they're at on the table. So let's predict some bond types. So the first one to look at is the bond between hydrogen and oxygen. So we're going to take hydrogen, which is 2.1, and we're going to find the difference between it and oxygen. So oxygen is 3.5, and like I said, we're looking for the absolute difference. So you're going to subtract those two from each other, and what you're going to get is me frustrated with my calculator because it is kind of late right now and I can't do that in my head. I know that's really sad. All right, so we get 1.4. So the way I've written it, it's actually negative 1.4, but like I said, it's the absolute difference. So we're going to get 1.4. That gets us between 0.5 and 1.7. So that means this bond is going to be a polar covalent bond. So go ahead and give these other ones a try. So you've got carbon and bromine. So find those two over here on our periodic table and do the calculation. Find out if they're going to be ionic, polar covalent, or covalent. Do the same for potassium and chlorine, and phosphorus and oxygen. And I will make sure that those answers are in the notes section of the PowerPoint for you to double check, but give those a practice. Oh, and one more, sorry, and calcium and oxygen. And we will pick up in our next lecture with more on ionic and covalent compounds with naming.